When you apply voltage to a circuit, it actually travels through the circuit like a wave. I've set up a wave machine here. As you can see, voltage travels through the circuit just like a wave. A wave machine makes it super easy to understand how the wave moves. But real-world circuits are trickier to understand. The reason is, unlike a wave machine, you can't really see the voltage in a circuit. So today I'm going to demonstrate how voltage moves through a circuit, just like a wave does. But first, a quick shout out to today's sponsor. If you're looking for low-cost PCBs, I highly recommend JLCPCB. I ordered the PCBs for today's experiment from JLCPCB. Recently, they've been putting a lot of focus on multi-layer PCB production, and they'd really like you guys to try their 6-layer boards. 5 100 by 100 6-layer boards are just $36.8. They also now offer Pad-on Via, an essential feature for high-density designs, at no additional cost. They're currently offering coupons for 6-layer boards, so now's a great time to try JLCPCB. Before we start the experiment with the electric circuit, let's first take a look at the wave machine. Here's the wave machine I made for this video. It lets us see how waves reflect and transmit at free and fixed ends, just like what we learned in high school physics. First, let's try it out with the free end. This part at the end can move freely. First, I'll move my hand to create a wave like this. The wave then travels forward along the machine, reaches the free end, reflects there, and finally comes all the way back to my hand. I'll skip the detailed explanation here, but the amplitude at the free end becomes twice as large as the original amplitude. However, this setup isn't perfectly ideal, so the amplitude is a bit smaller than double. And as the wave travels along, its amplitude gradually gets smaller. The amplitude of the wave I created gradually decreases as it approaches the free end. The wave reflected at the free end comes back in the same way through the upper part of the wave machine. This is how the wave travels down the line and reflects at the free end. Now, let's try the same thing with a fixed end. This end is fixed, so it can't move freely. Now let's give it a try, like this. Let's try it one more time, like this. The way the wave travels is the same as the free end we tried earlier. However, the motion at the fixed end is quite different. Because this is a fixed end, it cannot move. As a result, the amplitude at the end is 0. The wave reflected at the fixed end then travels back along the bottom of the wave machine toward where it started. With the free end, the wave travels back along the top. As we've seen, the way waves reflect at the end and the shape of the reflected waves are different between a free end and a fixed end. That is the most significant difference. Let me draw a diagram for each case. In the case of a free end, a wave is sent in and then travels along the machine like this. When it reflects, the amplitude at the free end becomes about twice as large. After that, the wave travels back, keeping the same amplitude as the input wave. So, what happens at the fixed end? The wave travels all the way to the end, just like it does at the free end. When it reflects at the fixed end, the amplitude is 0. The reflected wave travels back inverted. What went over the top on the way there now travels along the bottom. Next, let's try an experiment with an electric circuit and see how the waves move. We're going to use this circuit. This striped pattern you see is actually a 25-meter long copper foil. I input a signal here, it moves along the winding copper and eventually reaches this point at the lower right. I'm going to apply a pulsed voltage to this upper left point. Applying a pulsed voltage is basically like manually adding vibrations to the wave machine. I designed this circuit board to have a characteristic impedance of around 50 ohms. The impedance changes depending on the PCB's thickness, dielectric constant, and the copper foil thickness. In the wave machine I built, the characteristic impedance depends on the thread tension and the weight and length of the wooden sticks. As for the pulse voltage waveform, I'll input a waveform like this. First, let's try the circuit with the end left open. You can see that the waveform rises a bit slowly. This could be caused by losses in the cable carrying the pulse voltage or by inductance and capacitance in the circuit. The same thing happened with the wave machine. The wave being transmitted was a bit weak. Next, I'll measure the voltage at several points along the line, away from where the pulse was applied. The trace is 25 meters long. I'll check the voltage at 25%, 50%, and 75% along the trace, and at the end. First, the 25% point, about 6.25 meters from the input. The waveform looks like this. As you can see, the pulse travels along the line while largely maintaining its shape. However, the amplitude is slightly attenuated. This is due to losses in the line as the pulse propagates along it. That's why the amplitude is slightly lower. Let's look at the next one. Next is the 50% point along the line at 12.5 meters. The pulse travels along the line in the same way, and the waveform at this point looks like this. The shape is maintained, but the amplitude is even smaller. Now let's check the 75% point. It's the green one. The pulse has traveled even further along the line. By the way, it takes roughly 87 nanoseconds for the pulse to travel 12.5 meters. This pulse travels at roughly half the speed of light. We're outputting these very high-speed signals from a function generator and watching them on an oscilloscope. The green waveform at the 75% point has a peak here, followed immediately by another peak. This second peak is a reflected wave. You can also see a smaller reflected wave in the blue waveform at the 50% point. Now, let's look at the voltage beyond the 75% point here. This red waveform shows it. I'll gradually move the probe closer to the open end. As I do, an interesting phenomenon occurs. This is a reflected wave. I'm bringing the probe even closer to the open end. Now the amplitude has increased a bit. As we get even closer to the open end, you can see a spike in the waveform. And finally, we're at the end. What we're seeing here is the incident wave and the reflected wave overlapping. Because of this, the amplitude becomes roughly twice as large. Does this phenomenon look familiar? That's right, it's the same as the wave machine. In the free-end wave machine, the amplitude increased slightly at the end when reflected. The same thing is happening in this circuit. Let's shift the time base a little. First, we apply a voltage at this point. You can see the pulse waveform here. As the signal propagates along the long copper trace, it reaches this 50% point. The amplitude drops as it travels, but the shape stays the same. Then it reaches the 75% point along the trace. After that, it continues to propagate and finally arrives here. This red waveform shows the voltage at the open end of the trace. At the open end, the signal is reflected, and the amplitude becomes roughly twice as large. So where does this reflected signal go next? It travels back along the same path. Then we can see the positive reflected wave at the 75% point. Next, at the 50% point, this blue waveform shows the voltage. The pulse continues propagating back along the trace, moving all the way until it eventually returns to the source. As you can see from this waveform, the signal is quite attenuated. Next, I'll run the same experiment with a shorted end. This corresponds to the fixed end in the wave machine. Let's apply the voltage. Here's the waveform. At the injection point, the waveform looks the same as in the open-end case. Now let's look at the voltage at the 25% point. It looks the same here as well. Now let's look at the 50% point. The waveform looks the same here as well. Next, let's move on to the 75% point. The incident wave still looks the same at this point. But take a look at this. The waveform here looks quite different from what we saw in the open-end case. The waveform is flipped like this. This is the reflected voltage after reaching the short-circuited end, and it's negative. Let's move the time base a little. The incident wave comes in and is reflected at this point. The reflected wave is inverted, and then it continues traveling back along the line toward the source. So the pulse travels down the line, reaches the end, and then reflects back as a negative voltage. That reflected wave then heads back the way it came, and at the 75% point, the waveform is effectively inverted there. Further along, at the 50% point, this is what it looks like. At the 25% point, this is what you get. And back at the starting point, where the pulse was applied, this is the waveform. At the short-circuited end, the voltage reflects back as a negative wave. Now, let's take a closer look at the voltage near the short-circuited end. Keep an eye on the red waveform. The voltage moves forward. The voltage propagates forward like this, and you can see the amplitude starting to drop. As we get closer to the shorted end, it almost looks like the amplitude disappears. And finally, the shorted end. This end is at ground potential. It's directly shorted. So the voltage here is 0. As the voltage travels, the waveform gradually changes, and eventually it drops to 0 at the shorted end. Pretty interesting. I mentioned that the shorted end of the circuit corresponds to the fixed terminal of the wave machine, and that's exactly right. When a positive pulse is applied, it reflects off the shorted end and comes back as a negative wave. It behaves just like on the wave machine. I've shown that the way waves travel in electrical circuits is essentially the same as the way physical waves propagate through a medium. There aren't many demonstrations using a wave machine, but in electrical circuits we have something called impedance matching. When the medium changes while a voltage wave is traveling, the reflection and transmission of the wave also change. For example, if you make a section of the wiring thinner or thicker, impedance matching won't work anymore. Similarly, in a wave machine, if the rod's weight changes partway, the waves get reflected there because the medium changes. For example, if you attach a weight to a rod in the middle like this, the wave changes at that rod. This is the state where impedance matching is not achieved. When you actually use the machine, you can see that the rod with the weight reflects the wave. But not all of it is reflected. Some of the wave still gets through. So when impedance matching isn't achieved, the waves get reflected like this. But the key point is that some of the wave can still make it through even without perfect impedance matching. So what does it mean for a wave machine to have impedance matching? It means that if you set up another wave machine with the same characteristics and connect it, impedance matching is achieved at the connection point. The waves will keep traveling without reflecting at the connection point. I designed this electric circuit to have a characteristic impedance of 50 ohms. If you put a 50 ohm resistor at the end, the waveform won't reflect at all. Here's what it actually looks like. There's a slight deviation from the design values, so there's a little reflection. But compared to the open and shorted ends we saw earlier, the reflection is almost zero. I'm moving the probe closer to the impedance matched end, and here's what the waveform looks like. You can see there's no reflection at all. This is impedance matching. By the way, the reason the waves that reflected from the open or short-circuited end didn't get reflected again at the input terminal is that the input terminal was impedance matched. In circuits that handle high-speed signals, impedance matching is really important. That's because if the transmission and reflection of the voltage change, the waveform won't look like what you originally expected. For example, as a simple demonstration, if you touch the circuit, the impedance matching changes because of the resistance of your hand. It's really that easy to affect. Impedance matching is really important for cables like USB or HDMI that carry ultra-high-speed signals, and also for the wiring on PCBs that handle those signals across the board. If impedance matching isn't achieved, the waveform changes and data won't transmit correctly. Let's try a different experiment. I'm sending the same waveform signal from both the input terminal and the end terminal, and then something interesting happens. The waveforms are a bit tricky to read, but I'll use them to explain. The yellow waveform shows the voltage at the input terminal, and the green one shows the voltage at the end terminal. Here we can see the first peaks. This is the pulse voltage applied to the input terminal, and this one is the pulse voltage applied to the end terminal. After that, we can see another pair of peaks. Let me explain them in detail. First, the peak of the end terminal waveform. This is actually the pulse voltage from the input terminal that has been transmitted. As the voltage pulse travels along the circuit and eventually reaches the end, you can see it reflected in the waveform. Over here at the input terminal, we see another peak. This is the voltage pulse that was applied from the end terminal and traveled along the circuit. When it reaches the input terminal, this peak shows up. So, this pulse applied at the end terminal travels through the circuit and shows up here like this. We've been looking at the input and end terminals, but now let's check out the voltage at other points along the trace. For example, let's check the voltage at the 25% point. What happens now? This is the waveform. There are two peaks here. The first one comes from the input terminal, and the second one comes from the end terminal. Let's move the measurement point closer to the midpoint. Then we see a peak. Right now, I'm measuring the voltage at the midpoint. The amplitude is about twice as large. What's happening here is that the signals from the input terminal and the end terminal are overlapping, which increases the amplitude, as you can see. As we move the measurement point closer to the end, it looks like this. In the next experiment, we'll again apply signals from both the input terminal and the end terminal. However, this time, the signal will have its polarity reversed. The signal at the input terminal is positive, while the signal at the end terminal is negative. Now, you can probably guess what's going to happen next. First, the signal applied at the end terminal travels through the circuit and reaches the input terminal. It arrives with almost the same waveform as when it was sent. The signal applied at the input terminal also propagates through the circuit and makes its way to the end terminal. It arrives with almost the same waveform. I consolidated the waveforms. Let's take a look at the voltage at other points. For example, the 25% point. The signal from the input terminal has shifted, and the signal from the end terminal has shifted as well. Now, let's move the measurement point closer to the midpoint. We're at the midpoint now. The amplitude of the waveform is exactly zero, and the voltage here is almost zero. There are small peaks here and there, but this can vary depending on the measurement point. What's happening is that the signals from the input terminal and the signals from the end terminal overlap and cancel each other out. Let me explain using a diagram. When you apply a pulse voltage to the input terminal, it travels like this. We saw this in the experiment earlier. We also send a signal from the end terminal, which travels as well in the opposite direction. Then, the pulse signals collide right here at the midpoint. It looks like this. This causes the waveforms to overlap, which doubles the amplitude just like we saw earlier. This is what's often called the superposition of waves. After the superposition, the waves continue traveling in their original directions. The wave coming from the input terminal moves toward the end terminal, while the wave coming from the end terminal travels back toward the input terminal. This is called the independence of waves. We've looked at the superposition of waves and the independence of waves. If a positive voltage is applied to the input terminal and a negative voltage to the end terminal, it works the same way. The voltages keep traveling. The same goes for the voltage applied at the end terminal. And here, right at the midpoint, the waves overlap with each other. Even though they overlap, they cancel each other out because one is positive and the other is negative. As we saw, the amplitude is zero. After the overlap, the signal sent from the end terminal keeps moving along its path. And the signal from the input terminal also continues traveling in its original direction after passing through the overlap. In fact, the same thing happens with a wave machine. This video shows what happens when the same wave is applied to both ends. At the midpoint, the waves collide and overlap, which increases the amplitude. Then, since the waves are independent, each one keeps moving in its own direction. The same thing happens with waves of opposite phases. A positive wave is applied to the left end, and a negative wave to the right. When the waves collide at the midpoint, they overlap and the signal becomes zero. After the collision, each wave continues moving in its own direction. So today I conducted several experiments on waves. In these experiments, we could see that the waves in a wave machine and the waves in an electric circuit behave almost the same way and travel similarly. Well, there's actually one difference. The waves in an electric circuit travel at about half the speed of light. If you study waves in depth, you'll see how power transmission works. When lightning strikes a power line, a surge voltage travels along the line. As a result, equipment connected to the power system can be damaged. In my opinion, using a wave machine to explain how waves travel in an electrical circuit is a really good idea. You can take this as a reference. Thank you for watching. See you next time.